All right, so we're going to start by discussing what is integration. And we're actually going to start by kind of sidestepping the word integration and starting in a whole nother location. Okay, and that may seem like I don't make any sense whatsoever, but just kind of go with me on this. So here is some shape. Looks like it might be a parabola opening downward. It has two zeros. There's all sorts of information we can identify about it. We can say it has a maximum right here, it looks to be. It's increasing from negative infinity all the way up to whatever this value is. We can call this value b for the second if it helps any. We can say it's increasing from negative infinity to b, and then it's decreasing from b to positive infinity with a maximum occurring at x equal to b. This spot right here we can go ahead and say that 0, 0, and then over here we can say this is some point c0. We don't necessarily have to have all those values attached to it. Now, when we start talking about integration, the basic idea behind integration that we're building towards here is the idea that we want to find the total or the sum or how much is there. Whatever it is that we're counting here, that's what integration allows us to do. Basically, when it comes down to is that when we integrate, we'll just call this function f right here. When we integrate function f of dx, that gives us an area or a total or a sum or a amount. I'll just write it that way because it's all these different things. It could be a volume. There's lots of things that we could be measuring here that kind of fit this collection of answers. And this right here, this is the area right here, this whole space right here. So what integration allows us to do is be able to find how much space there exists between this curve and this line, or this curve and some other line even. And that's what we're kind of gearing after to try to do. Now, where do we start with that? Well, we're not actually going to start directly right here. What we're actually going to do, I'm going to go back and recreate that little shape I had here. And we're going to go back and say this is still C0 there. And over here, we're gonna pretend for a second that's at the point 0, 0, just because it makes this conversation easy to talk about. How do we find how much area is under there? Now, there are lots of ways we could do this. One way we could do this is when we say, well, this looks almost like a trapezoid. What if we were just to do that, or even bring it all the way over to here? Just assume that's a straight line, and we have that area right there. Well, a couple of problems pop up is how far up do we put these 2 points? We put them all the way up there. We turn it into a triangle. What's the length of this side right here? We'll call this base 1, and this is base 2 here. We could find base 2 easily enough. That's just the distance from beginning to the end of the interval. And in this case, that would just be c minus 0, which is a 0. So b sub 2 is c minus 0, which is just c. And then whatever b1 is equal to, right? But the problem with finding b1 is we don't necessarily know what those values are. If we did, that changes everything, but we don't necessarily know what those are. They're kind of arbitrarily spotted there. So it's not necessarily useful to just kind of stick a trapezoid in there. So what we want to do is we want to do this in such a way that is consistent, that's easily fixed and measurable and countable, ways that kind of remove a lot of the ambiguity for us. So again, we're going to go from 0 to 0 and c to c0 right there. And again, we're going to call this function f of x, right? But this time instead, let's do this. Instead of just doing some trapezoid or a triangle in there or whatever shape, let's just do rectangles. And not just any rectangles. Let's do rectangles in such a way that every rectangle shares a same characteristic beyond the fact they're all rectangles. Let's make every rectangle have the exact same width. Now, so we're automatically saying at this point that they're not similar rectangles. We're just saying they all have the same width. So the idea being is that I could simply cut this in half, and if you were to draw out 2 rectangles with that, we would have pretty close to an approximate area. But we could come along and we could say, let's cut that in half and cut those in half. And when we do that, And we can start, there's one rectangle, and there's another one, and another one, and another one, and there's one, and there's one, and there's one. And then the last one, of course, is right here to have an area of 0. So we count these up: 1, 2, 3, 4, 5, 6, 7 rectangles. Well, 8 if you wanted to, that last one just being 0. So there we go. There's a way. So that each of these rectangles, and what we're saying is that each rectangle has a width, and we'll call that width W. Every single one of them has a width of W. Now, if we were able to do that all the way across the board there, we would have a way, a nice consistent way, to be able to find the approximate area under the curve. So we'd be able to say that the integration from f of x dx would be approximately the area of those rectangles, right? Those rectangles that we have listed there that we find. Now, it is approximate because there are these little spots right here where we're overestimating and we're underestimating. Maybe they average out so we get pretty close to the exact value, but we don't know exactly if it is the exact value. But this is where we're going to start with this. So I'd actually like to run through a pretty quick example of this just to kind of give you what we're dealing with. And what we're doing here, this area process that we're doing right here, is what we call a Riemann sum. And that's named after a French mathematician, Riemann. Whether he came up with the exact process or not is kind of inconsequential. What's important is it's actually named after him. There's actually evidence to show that Galileo was doing this long before Riemann, but Riemann organized it in a different way. And of course, Newton and Lagrange put these stuff in. They were the fathers of calculus, and they put this stuff into a neat format for us that we now know as the subject of calculus. Okay, so let's do this. Some of you are thinking, oh, he's wasting a lot of paper. That's okay. Grow the trees so we can write the paper, right? So let's just say, let's do an actual example here. Let's say this is the function f of x. We're going to put some numbers with it. All right, do we have a real example to work with here? And if you ever wonder, like, how can I build a good, quick example of something? Look at what we got here. We have a 0 here and a 0 here. This 0 is 0. This is x equal to 0 right here. All right, and this is x equal to something else. What number do we want? Say 4. 4 is a good number, right? So there's my two zeros. So there's x and x minus 4. There's my two zeros for my function, right? But the thing is, this thing is opening downward, right? So we just put a negative in front of it, and now it opens downward. Woohoo! Right? So we could rewrite that as negative x squared plus 4x. Now we have a function, all right? Now, what can we do with that? Well, let's just say that we want to find the approximate area between x equal to 0 and x equal to 4 using, let's say, 8 subintervals. All right, so what does that mean? Well, now what we need to do is find the width. Well, how do we find the width? Well, it's the starting and the ending of the interval, which I actually said and wrote backwards, right? So it's the end of the interval minus the start of the interval divided by how many subintervals we want to create. And that's going to tell us that's 4 over 8, or each one is 1/2. So when we draw out our widths for our rectangles, they'd be 1/2 in width each, right? Now the next thing we need to think about is, well, how are we going to line these up? Are we going to line these up so that they touch like that? And then the next one would be right there. So if we're doing that, we need to think about, well, how do we find that corresponding height there and that height? Because that's y1, that'd be y2, and on down the line, right? Those would be y values. Well, what I need in order to find the y values would be the x values. And the first thing that pops in your head maybe is, well, I don't know the x value right here. But we do know the start of the interval, and we do know the width. And at this point right here, we've moved over one width, right? So the x value for that first value, so y1 would be f of 0 plus 1/2, 1 width, right? And y2 would be the function 0 plus 1/2 times 2, because it'd be 2 widths over, because there's another width, right? If we go over to the next one here, and these aren't being drawn very evenly, are they? There's another width, right? So y3 would be the function starting at 0 and then moving over 3 widths. Now if you notice, all we're doing there is, I could come back and say, well, this is times 1, right? Notice 1, 2, 3, 1, 2, 3. So to find any particular height, right? Instead of y, we could actually talk about that being the height there. To find any particular height, that's going to be the function starting at 0 and moving over so many widths, like that, right? Which is pretty cool. So now you have this generic way of finding each individual value, right? So we could find all the widths at this point. We have the function up there. All we got to do is plug in the values, and what we're saying here is f of 1/2, f of 1, f of 1.5, f of whatever that is, right? And we just plugged all those in. Now, then we find the individual areas, right? So we define the areas, which is going to be the approximate area under the curve, not the exact areas, but we're finding these areas. We're just going to need to add area 1 and area 2, area 3, area 4 out on the line. And each one of those is found by doing width times height, right? Width times height 2, width times height 3, and on down the line until you get to the width times height 8, all right? Notice that all the widths are the same. So you're really talking about this being width times all the heights. I don't need it way over there, do I? Okay, so all my heights added together. So all I really need to do is identify all my heights, add all my heights together, and then just multiply times that width. So I already have most of the pieces here that I need. So that is going to be 1/2. And then the first one is 1/2 plus 1 plus 1 and 1/2 plus 2 plus 2 and 1/2 plus, made it a little messy there, sorry about that, 3 plus 3.5 plus 4. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. There we go, right? And if you're wondering, like, how did you find all those values? Well, there's something I did wrong here. I hope you saw that. These are just all the x values. I need to do f of each of these, right? So it needs to be, let me try that again. It needs to be f of 1/2, because that was just an x value, and then f of 1, and then f of 1.5, right? And f of 2, and on down the line, all the way to the point where you get to f of 4, right? And then we just add all those values together, multiply it times 1/2, and that would give us the area, which would be the approximate area under the curve. This would be the Riemann sum that we did right here, okay? We would have found the Riemann sum, and that would be approximately the integration of f from 0 to 4. And we're going to do that second part as well, so don't just think we're just kind of ignoring that. But this is where we're starting to kind of give us some background of what the processes are that we're going through with this. All right. Now, I'm purposely not finishing this part because I am kind of reaching my 15-minute mark, and I want to honor that time period, but I am going to go through this in a little bit more detail, where I'm actually going to finish this in part 2. And so you can see how this actually works, and I'm actually going to extend this out into a more generic version of this so we can work about this, and I'm going to actually add some more details in front of this word Riemann right here, because there's more things that go along with that. All right.